Here's look at this question. What percentage of cases has a score between 71.7 and 90.6? 90.6. Again, we solve this problem based upon the characteristics of a normal distribution. Let's lay out this distribution. For this distribution, the mean is also 78 and the standard deviation 6.3. Okay, now what percentage of cases has a score between 71.7 and 90.6? Okay. What percentage cases lie between these two values, 70.7 and 90.6? Okay, we need to find the size of this area. Now, size of these areas had to be determined one at a time. It's a combination of two slices. From the mean to 71.7 is one slice, and from the mean to 90.7 and 90.6 is another slice. If we know the size of two slices, we just combine them to find the entire percentage. So the way to find the solution to this question is to find two slices separately, then we combine them to find the total percentage for cases to fall between 71.7 and 90.6. Now let's do one at a time. 71.7 to find the percentage from the mean to 71.7. Let's use this chart as a guide. We know from the mean to one standard deviation, you should have a 34.13%. So now we need to figure out between 78 and to 71.7, how much it is. How many standard deviation is it? Is that one standard deviation or the two standard deviation? How do we figure that out? There's a simple way to figure that out. We use 71.7 minus 78 divided by the standard deviation. 71.7 minus 78 divided by standard deviation, that gives -1. 1 means one standard deviation. -1 means below the mean. So we know that 71.7 is one standard deviation below the mean. If that's the case, what should be this percentage? One standard deviation below the mean, that should correspond to 34.13%. What about here between the mean and the 90.6? Again, we use same method to figure out 90.6 is how many standard deviation above the mean. Okay, so we have to figure out 90.6 is how many standard deviation above the mean. We use 90.6 minus 78 divided by the standard deviation. That gives us a positive 2. 2 standard deviation. And positive sign means it is above the mean. So for the mean, 2 standard deviation above the mean, it should have half of the 95.44%. Okay, 47.72. Okay, so this slice is 47.72%. Now you combine the two slices together, you obtain the value 81.85%. So that's how we can do this type of calculations based upon the characteristics of a normal distribution. Now, in in-class activity number 8, you can get more opportunities to practice this type of calculation. So you can go ahead to do the in-class activity number 8, and also you do the assignment number 8. So those are basically calculations based upon the characteristics of normal distribution. Especially, you can use this chart as a guide in your calculations. Okay. Now we solve one issue. We understand the basic characteristics of a normal distribution and what gave a normal distribution its unique bell shape. Now let's look at this issue. This is the example we see previously, and this is a place that has annual precipitation. In the last 60 years, we see that the annual precipitations conform to a normal distribution. And we know that given the mean on 45 corresponds to one standard deviation, between the mean between the 40 and the 45, you have 34.13% of all cases, and between 30 is 2 standard deviation below the mean, and between 30 and 40 you have 47.72% of all cases. So this is one specific normal distribution for the place. Then also for the same place, we know that in the last 6 years, the annual temperature also conform to a normal distribution. The mean is 67 degree Fahrenheit, and the standard deviation is 8 degree Fahrenheit, and then we know the 75 is 1 standard deviation, and between 67 and 75 you have 34.13% of all annual precipitations of the last 60 years, and between 43 and 67 you have 49.87% of annual precipitation over the last 60 years. And so for each variable that conform to normal distribution, we can draw a chart as this to show the percentage of distribution. And you have 2 variables, we can draw 2 charts, 3 variables, 3 charts, 100 variables, 100 charts, 1,000 variables, 1,000 different charts. That appears to be inconvenient, because every time when you have a normal distribution, you have to draw a separate chart to show between the mean, between what specific mean and what specific values you have 34.13% of cases, and that's not very convenient. What we can do here is to find what things are in common between these 2 charts. Let's find out what things are in common between the 2 charts. Okay, let's see. 40 is the mean. 67 is the mean for different charts. Okay, on this chart, 45 is 1 standard deviation above the mean, above 40. 50 is 2 standard deviation above 40. 55 is 3 standard deviation above 40. 35 is 1 standard deviation below 40. 30 is 2 standard deviation below 40. 25 is 3 standard deviation below 40. Okay? So 3 standard deviation below 40, 2 standard deviation below the mean, and 1 standard deviation below the mean. Now look at this chart. 67 is the mean. 75 is 1 standard deviation above the mean. 83 is 2 standard deviation above the mean. 91 is 3 standard deviation above the mean. In the same way, 59 is 1 standard deviation below the mean. 2 standard deviation below the mean. 43 is 3 standard deviation below the mean. Have you found anything common here? Have you found anything common here? Although each of these values is different from each other. 40 is different from 67, 35 is different from 59, 30 is different from 51, 25 different from 43. They are not comparable because they are different values, they have different units, they refer to different things. But one thing in common among each pair of these numbers, that is, they are the same units of standard deviation from their own mean. You see that? One standard deviation below the mean, one standard deviation below the mean, two standard deviation above the mean, two standard deviation above the mean. These are the things that are common between the two charts. Now, how do we express them? One standard deviation above the mean, two standard deviation above the mean, three standard deviation above the mean. 35 is one standard deviation below the mean, 30 is two standard deviation below the mean, 25 is three standard deviation below the mean. 0 means 0 standard deviation from the mean. It is the mean. So 0 means that this value is 0 standard deviation from the mean. Now, before the change, we labeled those values referred to the precipitation measured in inches. But now, after we change those values to the number of standard deviations from the mean, we just labeled as standard deviation. Standard deviation. What about this? 75 is one standard deviation above the mean. 83 is two standard deviation above the mean. We can go through this again. Now we realize that we can label all this in the same way as we labeled this. We use how many standard deviations they are from the mean. How many standard deviations they are from the mean. That is something that are common between the two charts. We can label all these different values in terms of how far they are from the mean in terms of standard deviation. And we can label these two charts with these things that are in common between them. The number of standard deviations of each value from the mean will label this chart. We can also label this chart by using the number of standard deviations from the mean. Now, before we change this label, two charts, they are not comparable. Values are different, units are different, but now they are comparable. Did you realize that? They are comparable. Now they have the same numbers. They're comparable. 75 is comparable with 45 in terms of the fact that both values are one standard deviation above their own mean. 30 and 51, now we know their relationship. They are both two standard deviations below their own mean. We can do the same thing for thousands of all these normal distributions in the real world out there. To label all of those charts, normal distribution charts, by using this system. How far each of those values from the mean in terms of standard deviation. And this is called standardization. Standardization, we use standard deviation to relabel all these charts to come up with a common chart like this. In this chart, all these places are labeled not by the actual temperatures, actual precipitation, actual income level. No. We'll label all these places by telling how far they are from their own mean in terms of standard deviation. In terms of standard deviation. And Z is the standard deviation. We use the Z, so-called Z-score. Z-score is 1, means this is one standard deviation above the mean. Z-score is -3, means that this place is 3 standard deviation below the mean. Now we convert all these hundreds of thousands of millions of different standard deviation in the real world with their own units, with their own context, into one single thing, the standard normal distribution chart. the standard normal distribution chart. So this process is called standardization. How did we do this? How do we convert the value from the original score into the standard score? Okay, it's very easy. So this 55 corresponds to 3 standard deviations above the mean. You can simply use 55. Now, if you follow me, 55 minus the population mean divided by standard deviation. Do you have a calculator? Let's do the calculation. 55 minus 40 divided by 5. What do you get? You got a 3. Good. 30 minus 40 divided by standard deviation. What do you get? -2. Now, 75 minus 67 divided by 8. You have 1. And now, 51 minus 67 divided by 8. You should have -2. So that's okay. For all these different normal distribution, if for each one of those distributions we use a specific value in the distribution minus the mean of the distribution divided by their standard deviation, that should tell you how far they are from the mean in terms of standard deviation. Okay, that's where you got 55 correspond to 3 standard deviation above the mean. 51 is correspond to 2 standard deviation below the mean. Oh, that's how we come up with this common theme among all those different normal distributions in the real world. Okay, that's how we come up with these standard normal distribution charts. And specifically, this is called z-score, the standard score, or normal distribution of standard normal scores. This score is calculated by using this formula. This formula on the top is x minus mean. What is x minus mean? The value of a particular variable minus the mean of the variable. What is this? We know this concept before. This term is called deviation. Deviation refers to the distance of a particular value from the mean. At the bottom is the population standard deviation. Is the population standard deviation. Mu is the population mean. So the value of particular variable minus the population mean, this is a deviation divided by the standard deviation. Standard deviation refers to the difference from the mean for the entire group. For the entire group, deviation is the distance from the mean for a particular value in the distribution. So the distance from the mean for a particular value divided by the distance from the mean for the entire group, that gives us the standard score, give us a z-score, give us a sense of, for this value, how far it is from the mean in terms of standard deviation. Okay, it measures how far a particular value is from the mean in terms of the standard deviation. So now we know the advantage of using the standard score. Come back to the chart. So you convert all different real-world variables that conform to normal distribution into this z-score and to build this particular standard normal distribution. And this standard normal distribution corresponds to what we have learned early on. Remember, early on we summarized within certain standard deviation of the mean, you have a certain percentage of cases from the negative 1 to the positive 1, you have 68.26% of all cases negative 1. At that point, we said that it's one standard deviation below the mean to one standard deviation above the mean. Now we can simply use, say, the z-score is negative 1 to z-score positive 1. This is the same thing as one standard deviation below the mean to one standard deviation above the mean. So we already know this. Now we just come back to understand this in a new context. And this one standard deviation below the mean is represented by the negative value negative 1. See, this corresponds to this. This corresponds to this. And this corresponds to this. And this corresponds to this. Okay? So if we know for a particular value how far it is away from the mean in terms of standard deviation, we can use this chart to determine the percentage of distribution. For example, if a particular value, a particular temperature that is 2 standard deviation above the mean, then we know that between that temperature and the mean, you should have 47.72% of cases in the last 60 years that are lie in that interval. So that's a pretty useful tool to know. Okay. So this process is called finding the standard scores or standardizing the variables. We convert all the real-world variables into this z-score. Try to know how far each of the values in those variables from the mean in terms of standard deviation.